Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to alternating voltage and current. So previously we discussed the mean or average value of alternating current and voltage. Here we'll discuss in detail about the root mean square or RMS value of alternating current. First alternating current and then alternating voltage. So before that, a quick review of what alternating voltage and current is. As we have already discussed, an alternating quantity, whether it is a voltage or a current, is a parameter which, the two important aspects, magnitude and direction, they change with time. The magnitude, it continuously changes with time, while the direction, it reverses periodically. The polarity of voltage and the direction of current, it reverses periodically after a fixed interval of time, which is called as the time period. Now when an alternating voltage is applied in a circuit, it results in the flow of an alternating current. Now the alternating voltage is expressed by its instantaneous value at any time t, which is given by Vt is equal to Vmax sin omega t, where Vmax is the amplitude or peak value, omega is the angular frequency. This is with no initial phase angle taken into consideration. So when phase angle is taken into account, it becomes omega t plus minus phi. Just plus minus phi is included here. Plus for leading phase angle, minus for lagging phase angle. This is the waveform of any alternating quantity. This is for voltage, and similarly we can express current by its instantaneous value in the same way. Just instead of V we have I. Here it is IT is equal to I max sin omega t, and IT is equal to I max sin omega t plus minus phi, and this is the waveform. Now just like we discussed in the mean or average value of alternating voltage and current, the two things, the two parameters that we discussed, the mean or average value and the root mean square value, what they try to do is to give us an equivalent DC representation of the AC signal. We have a AC signal here, a continuously varying and periodically reversing signal here. If we want to express it in terms of a steady parameter, a steady quantity, a DC quantity, what will be the equivalent representation? That is, if we try to measure charge, the amount of charge flowing through the circuit, that gives us the mean or average value, the amount of charge transferred. In root mean square value, here we measured the heat energy produced because of the application of the AC voltage and the flow of AC current. Okay, here it is charge transferred, the total charge transferred, Q. Here is the heat energy produced, H. Okay, now we discussed root mean square value in the similar manner as the mid-ordinate method, where we consider a signal, any half cycle, and we divide it into equal parts on the time axis. The width of each part is the same on the time axis. The middle portion of each part we call the mid-ordinate value. This is for current. If we have voltage, it will be the voltage mid-ordinate values. And then we take these mid-ordinate values and calculate this, the RMS value, which is given by, for current here, I1 square plus I2 square plus I3 square plus IN square by N, where I1, I2 and I3 up to IN are the N mid-ordinate values divided by the number of mid-ordinates. Similarly, for voltage, the voltage mid-ordinate values are taken. Similarly, we take V1 square plus V2 square plus V3 square plus Vn square by N. So here there is square root. So root, we have taken the average of the squares, so mean, and we have taken the square, that's why square root mean square value. We have discussed it already previously in different values of AC, where we also discussed peak value and peak to peak value. So here root mean square value, if we are trying to discuss why the need of root mean square value arises. We have already discussed mean or average value, but the problem with mean or average value is that if we take one complete cycle, the average value, it becomes 0, because the positive half cycle is exactly equal in magnitude to the negative half cycle, and it is opposite in direction. So that's why the positive and the negative half cycle values, they cancel each other. That's why for average or mean value calculation we only take one half cycle, half the time period. So it cannot be used for power calculations. The mean or average values, they cannot be used for power calculations. So in order to include power calculations, we have to include a suitable criterion which takes into account the entire full cycle, complete cycle from 0 to t. The entire positive and negative half cycle, entirely it is taken into consideration. So here root mean square value comes into play. So as I said, for mean or average value we include charge transferred, whereas in root mean square value we measure the heat energy produced in the circuit because of the application of alternating voltage or the flow of alternating current. So the amount of heat produced in a circuit consisting of a resistor R because of current I or voltage V is this: H is equal to I square RT, H is equal to V square T by R. We know heat energy is equal to V I T, this. So we can write it as I square RT or V square T by R or VIT. So in any way you can express it. So if we are taking only current, then I square RT. If we are considering only alternating voltage, then V square T by R. So everything is to express this alternating current in terms of an equivalent DC value. So this root mean square value is the equivalent DC representation, steady value representation of this continuously varying signal. So this is the equivalent representation of this. So what is the definition by which we measure RMS value? So the definition of RMS value is the root mean square RMS, which is also called as the effective value or virtual value of alternating current, is that value of steady current or DC current which, when flowing through a given resistor of resistance, certain resistance for a certain period of time, produces the same amount of heat as is produced by the alternating current when flowing through the same resistance for the same time. So here the time which is taken is the total time period of the signal. The entire cycle, complete cycle is taken into consideration. So what we understand from this definition is that suppose we apply this alternating current for its entire cycle from 0 to t. Okay, if we apply this alternating current to this circuit, okay, then the amount of heat which will be produced in the resistor, it will be the same as this DC signal of RMS value IRMS. The value of this DC signal is IRMS, constant value. If we apply this signal also to that circuit, the same amount of heat will be generated. So this is the equivalent value, and this RMS value is given by I max by root 2. Sorry. So Imax by root 2, which is equal to 0.707 Imax. So here we have represented the RMS value or root mean square value in terms of the alternating signal, the maximum value of the alternating signal, the alternating current. Okay, so this value is equal to how much in terms of the AC signal? It is Imax by root 2 or 0.707 Imax. So if this signal is applied for a duration of t seconds, which is the time period of the alternating signal, the same amount of heat H will be produced if we apply this alternating signal for the full cycle. It will also produce the same amount of heat H. So this is the equivalent DC representation. This RMS current waveform is the equivalent DC representation, DC equivalent representation of this AC signal. Okay, this. So DC representation of the alternating current. So this and this are equivalent, they are the same in terms of the amount of heat which is produced in the circuit when both these signals, current signals, are applied for a duration of t seconds. Here also the full cycle is t seconds, here also this signal is applied for t seconds. So this and this, they are equivalent. Okay, this is just the DC representation of this AC signal, and this is the AC representation of this DC signal. They are equivalent. Okay, so the essence of mean value and RMS value calculations is to represent equivalent DC representation of the AC signal. But in mean value, we only take half the time period. For mean value, we only take half the time period, one half cycle. In RMS value, we take the full cycle t. Okay, this is the only difference. Okay, so now we will derive how we got this value of IRMS as Imax by root 2 or 0.707 Imax. Okay. So now we'll discuss the mathematical derivation of the RMS value of alternating current. Okay, so RMS value of alternating current. So let us say we have this circuit. This is the alternating voltage, this is the resistor R, and this is the alternating current IT. So here we are determining IT, so our focus is the alternating current, the instantaneous value IT. Okay, so what we are trying to do is, let us say this is the alternating current. Okay, 0 t, the full cycle Imax minus Imax, and let's say this alternating current, the instantaneous value is expressed as IT is equal to Imax sine omega t. Okay, this is the expression, the instantaneous value. Okay, now let this current flow through this resistor R because of this alternating voltage applied. Okay, so what we are trying to do is to determine an equivalent DC representation. Okay, this is time axis, this is IT. So our objective is to determine an equivalent DC representation of this AC current signal. So that we are calling IRMS. So by definition, the condition is that both these signals, when applied for this duration t seconds, they produce the same amount of heat in the circuit. So the heat produced here is given by IT square RT. Okay, this heat produced because of the AC signal and the heat produced because of the RMS value, the DC equivalent representation, they should be equal. Okay, for t seconds. That is the basic definition of RMS value. So now let's say we are considering this instantaneous value of the alternating current. Okay, so let this current IT, it flow for a small duration dt. Okay, this IT flows for a small time duration dt. So the amount of heat, small amount of heat dH produced in this time duration dt will be IT square R dt. This IT square R dt, because heat energy is equal to I square RT. So the total heat produced H will be the integration of dH from 0 to H, the full value, and this will be integrating this expression over the entire time period, full cycle, 0 to T. In mean value we used to do from 0 to T by 2, here it is from 0 to T. So IT square R dt. T square R dt, which is equal to, we can write it as integration of 0 to T I max sine omega t square R dt. Okay, okay, this can be further written as is equal to, we take I max square and R outside. Okay, so it will be I max square R integration of 0 to T sine square omega t dt. Okay, this, because I max square R, they are constants. Here we are integrating with respect to time. This is the only function with respect to time. Okay, so now we will write sine square omega t as, it will be I max square R integration of 0 to T, and this will write it as 1 minus cos 2 omega t by 2 dt. So here we know that sine square theta is equal to 1 minus cos 2 theta by 2. So using this we have substituted sine square omega t as 1 minus cos 2 omega t by 2 dt here. So here it becomes I max square r by 2, taking outside the integration. So here it is 0 to t 1 minus cos 2 omega t dt, which is equal to I max square r by 2 into, this is integration of 0 to t dt minus integration from 0 to t cos 2 omega t dt, this. Okay. So now we can write it as, that is equal to I max square r by 2, integration of dt becomes t with upper limit capital T, lower limit 0, and this is 1 by 2 omega sine 2 omega t. Okay, because here 2 omega behaves as a constant because we are integrating it with respect to t. So only t is the variable. So upper limit capital T, lower limit 0. So here it is I max square r by 2. Here it is t minus 0, capital T minus 0, and here it is minus 1 by 2 omega sine 2 omega capital T minus sine 0, because when we multiply here, substitute t here 0, it will become 0. So now here if you see, we know angular frequency omega is equal to 2 pi by capital T, where capital T is the time period, or we can write it as 2 pi f, where f is the frequency in hertz, t is time period in seconds. So if we take this into consideration, omega t is equal to 2 pi, omega capital T is equal to 2 pi. So here it becomes sine 2 pi t becomes sine 4 pi. Okay, so this will be I max square r by 2 to t minus 0 minus 1 by 2 omega sine 2 into 2 pi, that will be 4 pi minus sine 0. So this entire thing will be 0 because this is also equal to 0, this is also equal to 0. So we'll only have I max square r t by 2, I max square r t by 2. Okay, this is the final value. This is the amount of heat which is produced, the amount of heat which is produced because of the application of, or the flow of the alternating current. Okay. Now if IRMS is the equivalent DC representation. Okay, IRMS is the equivalent DC value or DC representation of AC current. Then by definition, the amount of heat which is produced because of the flow of this IRMS, that will be the same as this. So that heat is equal to IRMS square RT. So according to the definition of RMS value, this and this should be equal. Okay, so here that implies IRMS square RT is equal to I max square RT by 2. So RT will get cancelled. That implies IRMS square is equal to I max square by 2. That implies IRMS is equal to I max by root 2, which is equal to 0.707 I max. This is the RMS equivalent value of the alternating current. Okay, so this is the amount of heat. All this derivation which we did here, this is for the amount of heat which is produced because of this AC signal over the entire time period from 0 to t. This thing here, this one, all this value, it is for this amount of heat produced because of this. Now IRMS is its equivalent DC value. We are trying to represent this AC signal in terms of some DC value. So by definition, if we apply IRMS for this t second duration, this will also produce the same amount of heat. That is the definition of RMS value. So here we just equated the two values. Okay, this is the amount of heat which is produced by AC in time duration t. Okay, and this is the amount of heat which is produced by the equivalent DC value in t seconds. So we equated both them and we got the RMS value as I max by root 2, which is 0.707 I max. Just we equated the both of them. Okay, so we got the result, the value.